we introduce FaVoR, a new 3D representation for feature descriptors that utilizes trilinear interpolation exclusively for volumetric rendering on voxel grids. FaVoR represents persistent landmarks in a scene using voxels, enabling feature queries from novel viewpoints at test time. This facilitates an iterative rendering and matching pipeline, improving data association and ultimately enhancing camera pose estimation via PNP. Unlike conventional feature matchers that extract and match features between a target and query view, FaVoR renders features for novel views, allowing iterative refinement of the camera pose, leading to more accurate camera relocalization. Our method sparsely represents a scene by triangulating points tracked over a sequence of frames. Then it associates a voxel with each 3D point to create a local dense rendering of the corresponding feature descriptor. By doing so, FaVoR enhances matching capabilities for unseen views while avoiding the computational burden of a full dense scene reconstruction. Visual localization has been widely studied, and existing approaches can be broadly categorized into four main methodologies. Methods that directly regress the camera pose from an image after being trained on a test set for a specific scene. For example, Lens by Moreau et al. Demonstrates how neural rendering can make this process more robust by generating data from unseen views used to train the pose regressor network. Other methods after being trained on a test set use neural networks to directly regress the 3D structure of a scene given a query image and then localize using 2D-3D correspondences, such as ACE by Branchman et al. Hybrid methods, on the other hand, build a sparse 3D map and hierarchically associate landmarks with full image descriptors for 2D-3D matching at test time, as demonstrated in HLOC by Sarlin et al. In recent years, robust 3D neural novel view rendering has led to methods that directly learn to render novel views of visual features. Examples include Crossfire by Moreau et al., which learns a dense 3D representation of feature descriptors for a given scene, but struggles to scale to large environments. Similarly, NerfLock by Liu et al. Uses dense NerF-based scene reconstruction and depth information to synthesize novel feature descriptors, but it also bears the burden of building a dense scene. Finally, FQN by Germain et al. Trains an MLP to learn a sparse set of descriptors that can be queried using single ray tracing, but it faces scalability issues for large scenes and descriptors. Inspired by these prior works, FaVoR bridges the gap in the literature by proposing a globally sparse but locally dense feature representation. It requires no MLP or neural network training, relying solely on trilinear interpolation of a voxel grid associated with each tracked landmark on the test set. This approach allows FaVoR to scale to large scenes and descriptors, with a trade-off that memory usage depends on the number of tracked features. Now, let's explore the working principles behind the proposed approach. Given a sequence of frames, we detect and track feature points. For simplicity, but without loss of generality, we illustrate the process for a single point, as shown in the current image. For each point, we store its position in the camera plane, the camera pose it was extracted from, and a patch of the descriptor map centered at the key point location. We retain only points visible from multiple views to ensure good scene coverage with as few landmarks as possible. In this example, we use a short track of length 3. Once the point track ends, we triangulate the key points to find a 3D landmark in the scene. This process relies on known camera poses, which can be realistically provided by any robotic localization system, such as visual inertial odometry. After triangulating the point, we proceed with the voxel creation and initialization. For this reason, we project the extracted descriptor patches at the location of the 3D point. Here, for visualization purpose, the feature patch is represented using PCA compression, which reduce the high dimensionality descriptor into RGB space. The descriptor patch projection determines the size of the voxel grid we associate with the 3D landmark. Once the voxel size is determined, we optimize the voxel grid to render the observed views. This begins with ray tracing from the observed views. Then, we sample the voxel grid using trilinear interpolation, and the samples are used for volumetric rendering. The rendering produces feature patches, which we want to be as similar as possible to those observed during tracking. For this reason, we apply a loss function to minimize the discrepancy between the rendered and observed features. This process continues until a maximum number of iterations is reached. The voxel is retained only if it meets a peak signal-to-noise ratio quality requirement for rendering. We repeat these steps for each tracked feature in the scene, resulting in a sparse set of voxels capable of rendering features observed from novel views at test time. We evaluated our system on indoor scenes using the 7 scenes dataset, which includes environments with motion blur and illumination changes. We also tested on outdoor scenes using the Cambridge Landmarks dataset, which features large environments recorded at different times of the day with varying lighting and viewpoints. For evaluation, we rendered alike and superpoint features, covering descriptor sizes ranging from 64 to 256 channels, demonstrating the versatility of our method. Potentially, our method can be utilized with any other feature extractors. We present the median 6 DOF pose error for our method. In green is the best result, followed by the second best in orange and finally the third best in red. On the 7 scenes dataset, our system achieved top 3 results compared to existing methods for indoor settings, proving its effectiveness. For outdoor scenes, FaVoR performed slightly less accurately, ranking 3rd. However, unlike NerfLock, our system does not require dense scene reconstruction or depth priors. Additionally, we use significantly fewer feature points than HLock, as evidenced by our method's lower memory requirements. We compared memory versus accuracy for the largest scenes in both datasets. While hybrid methods excel in outdoor settings, FaVoR uses significantly less memory. In indoor settings, FaVoR shows strong potential, achieving one of the best trade-offs between memory and accuracy. We analyze the impact of different pose initialization priors on 6 DOF localization accuracy. Specifically, we compare 2 initialization strategies on the 7 scenes dataset, constant and retrieval. In the constant strategy, we use the first pose of the test dataset as the initial query image. As the target image moves further from this initial pose, the problem becomes equivalent to having a noisy pose estimate. However, unlike adding random noise, this approach is fully deterministic and reproducible, ensuring a fair point of comparison for future work. Retrieval, on the other hand, leverages dense VLAD to retrieve a more informed initial pose. We evaluate our approach using FaVoR coupled with a like-L, and measure median localization errors at different iterations of the render plus PNP ransack scheme. Despite starting from a less accurate initialization, our method consistently refines the pose and converges to low localization errors within just 3 iterations. This highlights the robustness of our approach to variations in pose initialization. Our approach presents a scalable and efficient solution for feature-based camera relocalization. Unlike existing methods, FaVoR requires no dense scene reconstruction, avoids neural network training, seamlessly integrates into existing robotics localization systems. Finally, our code is fully open source. Try it out.